Great. Yeah, thanks so much. And just to confirm, everything's working okay?
Yep.
Okay, cool. Yeah, so what I'm going to do in this talk is discuss 3 concrete vulnerabilities of machine learning models. And the reason we're going to look at these vulnerabilities is first and foremost for security and privacy reasons, sort of to understand, what can go wrong in these systems, but also because, as we'll see, sort of analyzing these worst case vulnerabilities can actually teach us a lot about how to make these systems better and sort of how they work under the hood. So let's jump right in. Okay, so sort of to start my talk, I want to think about kind of a cartoon mindset for how we might develop production NLP systems or machine learning systems more broadly. And sort of the first step to building these systems is, to kind of improve them until they're sufficiently accurate. So this is kind of what the machine learning community is, broadly kind of obsessed with doing, which is, tuning architectures, tuning optimizers, et cetera, until we build models that are sufficiently accurate for some task. And I think what's interesting now in, the year 2021 or, where we're at now is that we now have systems that are actually sufficiently accurate for many tasks. So whether that be machine translation, classification of images and things like this, we now have systems that, we can actually reliably maybe deploy in the real world and try to make some impact. So that'd be, of course, the next thing to do. Let's actually build a production system, based around a machine learning model and actually have real world impact or, make profit or whatever it might be. And I think really there's been an increasing realization that this sort of cartoon setup really doesn't tell the full picture. And that's for a few reasons. So one is the fact that there's many other factors we care about besides just the accuracy of our system. Okay, well, that might be the, for example, fairness of our system, maybe the efficiency of our system, or maybe also the security and privacy of our system. And all these factors are maybe equally or more important than actually having a system which is of sufficient accuracy. And maybe a more nuanced point is that we've realized that high in-distribution accuracy is really not enough to build systems that are robust and reliable in practice. And that's because there's often an inevitable distribution shift when we deploy systems in the wild. And models are often really brittle to things like a change in the domain of the inputs. Maybe models often work by doing things like memorizing common patterns or exploiting spurious correlations in the data. And all of this stuff doesn't really hold when you transfer to out of distribution data that's inevitably going to show up at test time. And what I'm going to do in this talk is really advocate for thinking about things from the worst case to study a lot of these questions, right? And as we'll call this is sort of an adversarial perspective. And that'll help us look at things like security and privacy, but also answer a lot of these questions around the robustness of our system and maybe get insights into how we can make them better, maybe what's causing some of these brittlenesses. So the sort of setup for everything in this talk is going to be around this kind of black box API-like interactions with systems. So imagine you have some system like Google Translate, though the same kind of idea kind of applies to many other types of machine learning models, where there's some private data that the company or organization or whatever it might be has created. They also have trained some fancy model, let's say it's some transformer system, but to the outside world, they don't really expose any of that details. They instead just expose a black box API that users can interact with. So for instance, a user could send some input and ask for the German translation of that input from a system like Google Translate. And this same kind of interaction where, just have this input output access to some sort of machine learning system is really the common way they're deployed. For instance, in things like fake news detection, I can upload some post onto Facebook, and Facebook will tell me whether that post has been flagged as fake or real news. Or for things like language models, I could provide something like an input, hey, do you, to a model, and something like the GPT-3 API will provide something back like the likelihood of that input, or maybe a likely continuation of that sentence. So in general, this kind of black box framework is, the way we should think about a lot of these vulnerabilities to models. And the reason it's interesting is because, it assumes the least amount of access that an adversary could have. All they can do is sort of query random inputs or maybe targeted inputs and see the model prediction back, but they don't actually know anything about our data set, about our model, et cetera. And so when an adversary does inevitably enter, what can they actually do with sort of this simple access to our system? And the main high-level takeaway from this talk and sort of what I'll be talking about is that adversaries can actually do a lot with just this simple access. Just by being able to observe the predictions and the classification probabilities from a system, they can actually learn a lot about things about the data of our system, about the model that we're using under the hood, and also how they could maybe change their predictions to change their inputs to actually change the model predictions. And so those are the 3 types of attacks that we're going to be looking at today. There's going to be things based on extracting training data from models. That is, we're going to try to reveal private information that might be underlying the training data. There's going to be attacks based on stealing the underlying model that might be proprietary or worked really hard on creating. And there's also going to be attacks based on controlling predictions of the target model. Okay, so with this setup, let's jump right into the first part of the talk, which is going to be around this idea of extracting training data from these systems. So the setup is, let's say I've trained some large language model or some machine learning system on some private data. Let's say it contains like confidential user information. Maybe I've paid a lot of money to annotate my data, so it's sort of proprietary, or other scenarios like this. And the adversary kind of wants to get their hands on some of my data. So I'm going to talk about this work called Extracting Training Data from Large Language Models, which is a joint work with Nicholas Carlini, Florian Tramer, and some other collaborators that we had this year at the Usenix Security Symposium. So as just a kind of background on these language model systems, which is what we're going to be attacking in this paper and also some of the papers we'll look at in a little bit. Generally, what these systems allow you to do is provide some sort of input to the model, and they'll provide back a likelihood for that input. Using the same mechanism, you can also generate from the model by, for example, picking the most likely token at each time step. And now we have these really accurate language models, things like GPT-3, which are able to generate really high quality continuations of sentences and also score sentences with really accurate likelihoods. And as I was just mentioning, a lot of these systems, whether they be language models or applications of language models, they're often trained on private data sets. So things like, for example, emails from specific users, or maybe things like medical data, or maybe other applications where the data underlying some system is actually maybe confidential, it's proprietary, or contains information that you don't want adversaries to know about. And a lot of these settings, we want to deploy and use machine learning, but we might be worried about some sort of these privacy risks that come with using such data. And that's what this attack will try to exploit and try to understand more. The other thing that's been happening in the language model space over the last few years is kind of this massive scaling of models, which I'm sure a lot of people have heard about. And that's both in the model size, the number of parameters that our systems are using, and also the amount of data that our systems are trained on. And what's interesting from this sort of scaling from a privacy aspect is that bigger models maybe are going to memorize data maybe more often, but also as we use larger data sets, we're actually decreasing the number of epochs that we're training on these data sets. So for instance, some large system like GPT-3 might have a ton of parameters, but also it's only doing one epoch of the training data. So in this sense, maybe it might be actually kind of really hard to extract or leak private information because our models aren't really overfitting that much. They're having actually really similar likelihoods on the training and test set. And that's just due to this nature of doing very few epochs on the data. So with that in mind, how could we actually launch some of these privacy attacks and what do they look like in practice? So when we're trying to extract training data, we're focused on these kind of private information, things, for example, like social security numbers that might be present in the data. So you can imagine some attack like I feed in something like Eric Wallace's social security number is, and then I try to generate from some system like GPT-3 and hope that the number that comes out is actually accurate. And how might one actually try to launch some of these attacks? So there's kind of this high level idea of how we could actually get data out of a model, but how is this even possible? And the main idea is what I was just talking about on the previous slide, which is this kind of thing about overfitting and memorization. So if we actually are able to exploit such overfitting and memorization, maybe we could actually identify inputs which are present in the target model's training set. And so the high-level way of extracting actually this training data is based on sort of just a simple two-step procedure that we're going to do in this work, which is based on the idea of first, let's just generate a ton of samples from the language model. So for example, we might provide inputs like Eric's social security number is, and then generate from the model. Or we might provide some other prompt that doesn't have to do with me, or maybe it's about some other entity, and we're going to generate many continuations of that input. But overall, we're going to get sort of a huge dump of samples that the model might have trained on and might not have trained on. And then what we're going to sort of do is kind of sift through this list of generations and try to find the ones that we think are in the training set and then ones we don't think are present in the training set. And the way we're going to do that is we're going to flag samples that have abnormal likelihoods, with the intuition being that If a sample is sort of abnormally too likely, that's probably a good sign that it was present in the training data. And the way we're actually going to do this sort of identifying of abnormal samples is a bit nuanced, and it can't just rely on this like simple overfitting, as we'll see on the next slide. So imagine you feed in some input like Eric's social security number is, and then some number continuation. And let's just say very informally, we say that the model assigns a medium likelihood to that input. So because the likelihood isn't super high, maybe we'll predict that the model, this input is not in the model's training set. Okay. Maybe if you provide some other input to the model, like FB URL or some random URL from the internet, maybe the model now assigns it a low likelihood, just because it's kind of a strange and weird input. Or if you provide some other input like J. Davis has cancer, the model says it has a high likelihood. In this case, we'll predict that it's probably present in the training set. So this attack will return one input saying J. Davis has cancer. The thing is, this attack has some accuracy, but it does often make a lot of mistakes. And the reason is because it'll often flag things like very simple, easy to solve sentences as in the training set, just because they're sort of naturally high likelihood under the model. And similarly, inputs that might be sort of a priori, very low likelihood, we're going to flag as not being present in the training set, just because they sort of have a low likelihood, regardless of whether you trained on them or not. And so the way you can sort of launch these privacy attacks in general, both for language models and for other systems, is based on this idea of sort of getting the natural likelihood of this sentence if you had not trained on it. So in particular, what you might think about doing is training some other system. For example, let's say we train some other language model. Let's say I'm going to represent it as a white box, just for the fact that I'm training it on my own end. And let's say this language model has been trained on some data I maybe scraped from the internet. So it's not any private data. I'm just kind of building my own language modeling system. And then what I use this language model for is kind of a reference point or a baseline of how likely should this input be if I hadn't trained on it. So for instance, I'd feed in something like Eric's social security number is, I provide the number, and then the model says a low likelihood. So if you compare this low likelihood to the target model's likelihood, which was a sort of a medium likelihood, we're going to actually predict that this example was probably in the training set because the target model is sort of disproportionately more likely than the reference model on this input. Similarly, for some input that wasn't present in the target model's training set, maybe both the target and the reference model assign it a similar likelihood. Or for another input, maybe our reference model assigns it a medium likelihood as compared to the target model, which had a high likelihood. In this case, then we'll predict it's probably present in the training set. So the whole idea behind these privacy attacks and the way you can get actually a lot of leverage is by checking the likelihood on some target sample and then comparing that likelihood to some reference model. So to see more quantitatively exactly of what these attacks look like, what I'm showing in this plot is on the x-axis is some target model's likelihood on some samples. And on the y-axis, I'm plotting some other reference model's likelihood on those same samples. And what we see on the y equals x axis, sort of generally following this trend of this line, is that most samples are scored pretty similarly according to the two models. But then there's sort of these outlier samples over here, which are ones where the target model thinks they're very likely, yet the reference model thinks they're very unlikely. And these are the sort of samples that you might want to investigate further as potential cases of this sort of memorization or privacy leakage in machine learning systems. And what I've color-coded here is sort of blue represents true positives that we've selected by our method, and red represents some false positive examples. So you can definitely see sort of as you get more toward these outlier scenarios, this is a much better. So let's look at exactly some examples of things that GPT-2 or models like this memorize and what these attacks actually look like in practice. So we run some attack results on a system like GPT-2 or GPT-3. It's not actually a model which has been trained on private data, but it is a language model which is large and representative. So it provides a good way of sort of doing a case study on some of these attacks. And what we find is that by and large, state-of-the-art language models are memorizing a lot of training samples. So for instance, what we did in this paper was we generated a small set of samples. We then filtered them down to a set that we thought was definitely in the training set. And we're able to find 604 samples that actually were verbatim memorized in a training set. And our attack accuracy is about 67%. So we identify something like 900 samples that we think are in the training set, and 600 of which are actually present in the training data. And so the types of inputs are kind of a broad range of different types of domains and topics and things like that that we actually extract. There's things like US news, which is a huge part of the training set. But then there's also some more concerning inputs, things like maybe URLs, maybe things like UUIDs or sort of personal information about users, or maybe their contact information, things like maybe their social security number or their phone number. So for example, we find things like personally identifiable information that we can reliably extract from the model. So here's a case where I've redacted their exact info, but we're able to generate someone's their location, their name, their phone number, their fax number, what company they work for, and things like this. We're also able to identify similar things like storylines that have real people's names. So in this case, this is talking about someone who's indicted for some sort of murder, and it has their real names, both the victim and the person who's accused of the murder. Similarly, we're able to find maybe more interesting things that are, about like Harry Potter pages or something like this, where the model has memorized, a large portion of the novel, or cases maybe that are maybe things about copyright or things like this, where the model has actually memorized raw source code from things like the Bitcoin client or video games. So these are cases where you can provide some sort of like code input to the model, and they'll actually generate some verbatim text that was present on the web. So these are both cases of sort of copyright types of things, and the previous ones were examples of maybe leaking personally identifiable information from models. One aspect of this memorization, which I think is super interesting, is how we can actually trace it back to the training data, and maybe what in the training data is actually causing the models to be abnormally likely on a sample. And I think what's interesting and perhaps most concerning is that in many cases, a lot of these inputs just show up once in the training set. So what I'm showing on the left are these sort of high entropy strings that we're able to identify and extract from a target model that are present in the training set. They're all varying length, but all of them show up in only one document in the pre-training data. So these are cases where, even though we're just doing one epoch of the training set, and even though, we're not overfitting really that much, and the fact that these inputs are kind of really strange, formatted, we're still able to reliably extract them from some model. So I guess the last thing I'll talk about in this section before I pause for questions is some ideas for how you might think about defending against them, and maybe some high-level takeaways for what the implications of this kind of privacy extraction from language models is. So in general, I think you might think about defending them by removing some of this private or easy to memorize data. So definitely a reasonable thing that most people suggest is we're training language models on these large data sets that might contain things like social security numbers or other things, and we might want to just kind of sanitize this personal information. So maybe we delete those inputs, or maybe we replace the social security number with some placeholder. And I think a lot of this stuff is very reasonable things to do, and often it won't necessarily hurt your accuracy of your system too much, depending on the application you're looking at. But in general, a lot of these sort of replacing and sanitizing information is really not sufficient to protect against all attacks. There's always going to be stuff that's going to slip through our filter, which adversaries might be able to identify and exploit. So in general, something that we've been working on, which I won't talk about here, is this idea of making your training process differentially private. And what this does is it basically limits the impact of any specific example on your language model or on your machine learning system. And that limiting of the impact actually prevents adversaries from extracting those data points. So in particular, it provides you some sort of guarantee, like if I do change one of the data points, so if I change, for example, a cat picture to a different cat picture, the model that is produced by my training algorithm is actually similar in those two scenarios. So I won't talk about too much of the details here. The high-level takeaway, though, is that often these differentially private training algorithms do hurt your language model utility, especially when we're talking about training systems at large scale. So right now, there's sort of this natural trade-off between this idea of protecting the privacy of the training data by doing things like differential privacy, and also being a high accurate system that has good downstream utility. Okay. So the last thing I'll mention in this slide before I pause for questions is some sort of takeaways about what are the actual privacy and legal ramifications for some of these attacks. So we see that a lot of these open source language models are memorizing text from the web. And of course, as I motivated, a lot of these problems are really big deals if your training set contains private information. And that's, I kind of think, kind of a no-brainer. If adversaries can extract social security numbers and things like that, that's definitely a bad sign. But I think also interestingly, something that we should be thinking about, as machine learning and NLP researchers, is what happens when we're using this public data and we're memorizing it and we're regurgitating it at test time. Is that sort of bad, and is that responsible data use? So for instance, I'll argue actually, yes, that there's a number of cases where, memorizing and regurgitating this public data can actually be kind of bad. For example, language models often output some personal information in inappropriate contexts. So for instance, I talked about this headline before about, some person named AD who was arrested for some murder. In this case, actually, AD is found out to be not the murderer. And the model still likes to generate a lot of cases that claim this person, did some bad thing, even though later they were found not guilty of this crime. And this is a great example, I think, of, how cases like things like GDPR's data misuse laws and other types of things come into play where, we're really not using a lot of this public data in a very responsible manner because our language models are actually memorizing it and maybe regurgitating this information at test time. Similarly, if you're looking at things like code blocks and things like this, a lot of this data is protected in copyright under US laws. And there's like an open question of, given that the fact that our models are kind of repeating and generating this copyright text, is that a case of copyright infringement? And do we actually have the ability to train these language models on these large corpora, without actually breaking a lot of laws? Okay. So just to wrap up what we've seen so far, we looked at this idea of extracting training data from systems. It's basically the idea of how can we feed inputs to models and get outputs that might be present in a training set. We've seen that language model samples do contain training text in cases where we can just kind of blindly generate from the system. And there's also privacy and legal questions, even when the data is public. And there's a bunch of open problems around how to mitigate this memorization without actually destroying the accuracy of our system. Cool. So I think I'll pause here for questions if people have them.
I think there's one in the chat where Rhea asked, I might have missed this, but how did you identify these memorizations initially? I.e., how did you know?
Yeah, so I guess what we're doing like practically in this attack is we identified a set of like 900 samples that we, according to this sort of abnormal likelihood metric, we thought were present in the training set. And then once we had those 900, we kind of retroactively checked our accuracy of if we had chosen these 900, how would we have done? And that's how we kind of got this like 604 number. So in this case, we're actually like querying the training set and just checking, of these 900, how many are actually verbatim present in there.
I actually wanted to ask, what is the privacy risk in like downstream models, which might have been fine-tuned on private data, which is probably a more tangible harm than LMs trained on publicly scraped data?
Yeah, this is a good question. We haven't looked too much into the fine-tuning aspect. I guess there's kind of like two things with fine-tuning. One is like, if I've pre-trained on private data, there might be a risk of that data being exposed downstream. Or if I'm maybe not pre-training on private data, I'm pre-trained on public data, something like GPT-3, but then I fine-tune on private data in the downstream task, there might be a further risk of privacy leakage then. And I think that's kind of the most common scenario that people are thinking about in practice, which is maybe I take a model off the shelf like GPT-3 or BERT or something like this. I fine-tune it on some task like sentiment classification, and then I use that model to perform predictions. And I think a thing that's concerning about a lot of that setup is when I do train on private data for downstream, I often have way less private data than I have public data. And that often means I'm doing a ton of epochs on this private data to try to maximize accuracy. So maybe I might have like a few thousand inputs to do classification on. I might do 10 epochs to that data. And naturally what happens when you do this is you end up overfitting actually a decent amount. And in these cases, launching a lot of these attacks becomes a lot easier. So I can, the accuracy, rather than only being 60%, might be, closer to 100%. And I might be able to identify, a much larger set of the training set. So I think in general, it's a bit tricky depending on, exactly the scenario, but I do think this kind of public pre-training private fine-tuning setting actually maybe has more risk than just like a private pre-training itself.
Do you think like you can still meaningfully extract this information when the objective is like classify positive or negative versus right now where you have an LM which can actually regurgitate words?
Yeah, people have looked at similar types of attacks in like image classification space where you try to find an example that leads to high confidence. I think one thing that's tricky there is like often what happens if you like try to directly optimize for inputs that lead to high confidence predictions in the model, you end up running to just like adversarial examples or other types of strange examples. So I think like one thing that's hard is like, how do you get the set of examples I want to check in the first place? In the language modeling case, we can just generate from the model. But in the classification case, it might be trickier to get a set of data points to check on.
Yeah, thanks.
And there's one more question about copyright stuff. So yeah, in general, when we're pre-training models like GPT-2 or GPT-3, we just scrape a ton of data from the web to train them. And actually under like US law, a vast majority of the internet is protected under copyright. So for example, if I just like tweet something that's like 20 words long and it's like my own words, that tweet is actually protected under copyright. Or anything like books or Wikipedia, a bunch of this data set, a bunch of these open data sets like this, a lot of stuff is protected under copyright, but it's available on the web to use. It's kind of a different question of, is it available on the web to use and can I scrape it, download it, and use it to train a machine learning model, which I then expose on the web. So I think there's this kind of still open legal question of, is it okay to use this private data or this copyright data, sorry, given the fact that my model might repeat it in some other form in a downstream use case. Cool. Final questions before I keep going? Okay, cool. Let's jump into the second part of the talk, which is going to be around this different problem completely around kind of stealing models behind APIs. So the kind of gist set up here is, let's say the adversary is interacting with some model and they want to actually steal the victim's model. So let's say, for instance, in the Google Translate setting, you maybe have a very expensive and proprietary system that Google has built where they've collected a ton of data, they've built some really fancy model, and maybe the adversary now, given these kind of black box interactions with the system, rather than trying to extract training data, as we looked at in the previous section, we're now going to try to extract the model weights itself. And you might want to do this, for example, maybe the adversary is trying to avoid your API costs. So they don't want to pay Google anymore for using Google Translate. Or maybe they even could go as far as launching a competitor service. So maybe they're going to launch, Air Translate or some other service, which, provides a similar service to Google Translate, but, uses a stolen off-the-shelf model. And so I'm going to talk about this work called Imitation, Attacks, and Defenses for Black Box Machine Translation Systems, which we had at last year's EMNLP. This is a joint work with two colleagues from Berkeley, Mitchell Stern and Don Song. So the kind of setup behind this model stealing idea that I talked about is that we want to train a model that imitates some black box API. So given the setup I talked about previously, you might think about trying to actually extract the exact weights of some target system. But really in practice, it's very infeasible to actually extract some exact setting of the weights from, let's say, the Google Translate API, given I know basically nothing. I don't know what the architecture is. I don't know like anything about their tokenizer, any details of their system. So instead, a much more feasible goal is to train a system that just imitates a black box API. And the way we're actually going to do this is by simply querying sentences to the API and then just using the API output as training data. So this is kind of a very simple idea, which is I want to mimic an API. Let me just collect a bunch of training data of input-output pairs of that API, and then just train my own machine learning model that kind of tries to mimic the API predictions. And this is very similar to this idea of model distillation, if people have seen that. But there are some key differences between the model stealing and model distillation setups. And that's mainly because first, we have no idea about anything they're doing. So like we don't know what architecture their model has. We don't know tokenizers. We don't really know much at all. We also don't even know the data distribution the model was trained on. So we might be sending these queries to the model, which it responds with very poor accuracy on the actual classification decisions, because we just have no idea what's in distribution and out of distribution for our queries. Nevertheless, what happens if we just try to maybe query like 5 million sentences to Google Translate, let's say, and just train our own system and hope for the best and see what happens? And actually what we're able to do in this paper is imitate a lot of these production models on common language pairs like English German, or maybe low resource pairs like English Nepali. And we're able to get very similar accuracies to these production models without spending much money at all. So in particular, if we measure BLEU score, which is a common metric for machine translation, for a couple different systems like Google, Bing, and Systran, which are 3 leading machine translation providers, we then trained our own system, which ends up being pretty comparable to a lot of these systems. Maybe it's a little bit worse, but all we had to do was query a few million sentences to the system and just kind of train our own model. And we only spent a few $100s on imitating all of these systems. So we really didn't spend that much money, especially relative to, I'm sure Google or these other companies have spent maybe millions of dollars on collecting training data for building some of these systems. We also see that if you measure things like out of distribution generalization, so maybe you test our system on a different distribution of queries that we actually provided to the model, we're also generalizing relatively similar to the target system. So we're not only being able to train an imitation model, which kind of mimics the target API in domain, but also it's kind of general and really does imitate the target model for a lot of out of distribution queries as well. And so in general, I think what we've seen is just that this problem of imitating models is actually pretty simple. We just train maybe the state-of-the-art model we can from some open source code base, but just plug in a data set that is pairs of input-output examples from an API. And so I think the big question with this model stealing is, what I've described isn't, necessarily super technical or anything too crazy to imagine, but it's really a very simple and practical attack. And I think, the big question here is, why is stealing so easy? So like something like Google or some system like this did actually, work really hard on training a model. They did work really hard on collecting some data set. And yet I'm able to get basically the same accuracy with only a few $100s worth of queries. And so I think the main answer to this question is that this idea of model distillation that I mentioned before really is a super robust and effective method. And that is to say, you can use a different architecture, hyperparameters, etc., from, let's say, the target system, and distillation will still work fine. Doesn't necessarily matter if I know the architecture or whatever it might be of the target system. I can just kind of train my own model, and it'll end up getting similar accuracy. And similarly, I could use maybe in-distribution data for querying the system and get similar out-of-distribution accuracy when I train my model, or vice versa also holds. I could actually query out-of-distribution data to the target model and also get similar in-distribution accuracy. So in general, these student models that I'm training from this distillation procedure, they actually end up mimicking a target model, very accurately. And I think this plot really does encompass a lot of the things I just talked about. What I'm showing in green and orange are essentially you can think of as very smart adversaries who query the right type of data, they have the right type of model, etc. But what I show in purple is what happens if an adversary is really dumb. They query very out of distribution data from the target model. They use the wrong model architecture. They maybe screw up some other aspects. What we see is that if you do query enough sentences, eventually you can mimic some target API. So the gray line shows the target API's performance. And with enough queries from the API, you're able to actually get a student model which actually imitates the target API with pretty high accuracy. And so the takeaway here so far has just been that if you do expose some system to an outsider where they can make sufficient queries to your model, whether it be a system like Google Translate or something like an image classifier or maybe a language model API, adversaries can steal your model with pretty high accuracy without really doing that much work. They just need to query a bunch of inputs, train an off-the-shelf system, and they're able to get pretty high accuracy. So I think a reasonable question is, well, hey, a lot of people are deploying machine learning models. Is it possible to actually protect my intellectual property? So like, is deploying a machine learning model behind a black box API actually just basically, effectively releasing that model to an outsider, which lets them, perform these type of attacks? And I think in general, defending against these attacks is actually very difficult. It's a setting where you know there's probably a neural network or some machine learning model behind the scenes. And now I just want to train a system, maybe another neural network model, which imitates that model. And as I showed on the previous slide, it's a very robust idea to perform this type of model distillation type of things. But there are a couple ways to make headway on kind of defending against other attacks. And the basic gist of what you can do in defenses is based on this idea of modifying my model output to actually hinder the learning signal. So what that means is kind of shown in the following picture. So the adversary who's actually training their imitation model is maybe running gradient descent, where they query some input to our system, they get some response Y, and then they actually run, let's say, gradient-based optimization on their model parameters using the output that my model returned. And what you can think about doing in this model stealing setting to actually defend against it is imagine a scenario where I had output some other translation or some other model output, let's say it's Y tilde, with the hopes that that translation actually screws up the optimization for the adversary. So the adversary is trying to do some gradient-based learning for some model, and I've kind of messed with the training data such that now the optimization kind of steers all over the place. So you could think of this maybe as like adversarially bad training data that is really hard to learn from the model. And so the way you can actually operationalize this idea of screwing up the training for the adversary is, let's say I, at test time, sample a bunch of translations for my model. So rather than outputting maybe the top best translation that I really like, I'll maybe get like a list of, let's say, 100 translations that I think are all reasonable. And then I try to output a sample that induces a very different gradient signal. So I'll try to maybe look through all the examples, and I'll pick the one that maybe I think if the adversary trained on would actually screw up their optimization in a large amount. And the technical details here are basically this idea of I kind of measure maybe a deviation between the gradient if I had trained on the original translation versus the translation that I'm actually going to output. And this sort of actually does, a pretty effective way of hurting a target model. So it does reduce your adversary's blue by actually a pretty noticeable amount. So 3 blue points is a huge noticeable amount. It definitely reduces the effectiveness of the system just because this data is kind of hard to learn from that I actually modify and output when I do this procedure. The difficulty and the challenge of this is that it's actually hurting my own blue by a noticeable amount as well. So just because this idea that I'm taking a machine learning model, I'm no longer outputting the top prediction. I'm outputting maybe its 5th best prediction or its 20th best prediction. It's going to be worse than my best prediction. So I'm going to take a kind of a hit in accuracy by trying to protect against these stealing attacks. So I think at the current moment, a lot of these stealing defenses, aren't really viable in practice, but you are able to make a little bit of headway in trying to stop an adversary by screwing with the input-output queries that they provide. Cool. So this is the end of the second part. In this part, we talked about this idea of kind of stealing models from APIs. We saw this idea that adversaries can actually steal models just because distillation is such a robust and simple tool. And also you can modify your outputs to the API, which can actually mitigate stealing, but it does come at a cost. And in this case, it's both a cost in accuracy, and I didn't mention, but it's also a huge cost in also the compute that you have to run at test time to actually find a reasonable output. Cool. So with that, I will also pause for questions on this portion.
I think there are 3 questions in the chat.
Sure, let me take a look. Okay, yeah, are queries expensive in practice? Yeah, so I think like a very practical way of defending against these attacks is to basically think about, okay, how much data would it take for someone to mimic my model? Let's say it's 1 million sentences. And let me just set the price of the API to be expensive enough that 1 million sentences of queries would actually be like prohibitively expensive. In practice, though, like it's not really viable to charge that much for the API. So things like Google Translate, they really don't charge a lot of money for a lot of these APIs, and you could a lot of these API calls, and you can maybe make 1 million queries for only a few $100s or tens of dollars. So in practice, I think we spent like under $1,000 for this entire project, and that's on like mimicking multiple types of services for multiple types of language pairs, and like it took also like multiple trials to get the details right for some of the experiments. So in practice, a lot of these queries are pretty cheap, I think, for some of these systems. Yeah, so someone also asked about an idea based on, rather than trying to actually stop stealing like in its tracks where I prevent the adversary from getting a model in the first place, you could also imagine some sort of defense where I just sort of maybe embed something into the adversary's model that I could then check later to see if it's present, and maybe then catch them red-handed that they stole my system. And this is a great idea that people have explored. Like one simple thing you could imagine would be when an adversary, maybe I detect that someone's trying to steal my system. And what I do is, instead of outputting my normal translation, maybe I output a very strange translation. And then when I find someone, who I thought stole my model, I then see if they produce that weird translation when I actually query their system. So in general, people call this idea like watermarking or similar types of ideas where I kind of embed some sort of strange output and then later try to check if the model recreates that output. And I think, I guess the last question is around, is distillation a way of defending against privacy attacks? I would say no in general. Like, I think if you, for instance, train a model on some private data, and then I guess this is kind of going back to the first part and also connecting with some of the ideas I mentioned, is like, if you train a model on a private data set and then you train, let's say, a second model which tries to mimic that first model's predictions, what can happen is it will also mimic the model in that it'll be overconfident for the training predictions as well. So I think in general, like a distillation model inherits a lot of the vulnerabilities that a private model also has.
Eric, I also have a question. So what if you think about defense methods on a much higher level? Like, for instance, you can have a CAPTCHA, right? Whenever people query for a translation, in that case, you will be able to tell whether, right, it's a computer that's making a query or an actual human. Wouldn't that be, because, in practice, in order to do knowledge distillation, you still have to have millions of data samples, which in this case, I think by either using CAPTCHA or limiting the number of queries each IP address can make. Isn't that also kind of a solution?
Yeah, I think in practice, a lot of these type of things are, you're really how you can stop these attacks is like either making your API more expensive, making it harder to query, adding checks to, for IPs and things like this, and rate limiting. And, a lot of this stuff in practice, I think, can slow or maybe stop adversaries in their tracks. Though definitely doesn't feel like the most elegant machine learning solution, I guess, to block it that way.
Yeah. I think there are two more questions coming in. First one from Varun: is it easier or harder to steal ensembles versus individual models, or it doesn't matter?
I don't know. I don't think it would matter too much, though. I actually think ensembles might be slightly easier to steal just because they're higher accuracy, but it's hard to say. And yeah, so for the other question, simple training. Yeah, I think like maybe I think one similar defense that you could imagine that's kind of related to this question is this idea where maybe when the person provides a query to my model, I then, let's say, randomly perturb my model weights at test time to output a different prediction each time. And kind of what the intuition behind this is like, what happens if my model is kind of constantly slightly changing? Doesn't that make it a lot harder for the adversary to actually mimic my system, because they're kind of bouncing all over the place trying to mimic different types of models? I think this is also a reasonable way of thinking about defending. I think it's very related to this idea of, screwing up their optimization by, jumping around with different types of models. I do think also it will probably have a similar effect of, hurting accuracy, where if you do jump around significantly, your system's probably going to be worse in accuracy and thus like maybe less effective in practice. Okay, cool, sounds good. We have about 10 minutes left, which is perfect. Let me jump to the third part. Yeah, so the last part will be kind of a short final wrap up part, which is on this idea of a completely different type of attack where adversaries are actually looking to control predictions from some system. So in this case, we're going to focus on a different application. We're going to focus on fake news detection or classification problems like this, where adversaries are providing inputs to systems, and they actually want to modify how your API responds to that system. Okay, so I'm going to talk about this work called Universal Adversarial Triggers, which we had 2 years ago at AMNLP. This joint work with people from Maryland and AI2. So the main idea of triggers is this idea of how can we sort of, and what can we do to kind of control predictions of some target API. So imagine, let's say I'm a hacker and I want to get some data onto Facebook that is fake news. And let's say the Facebook algorithm correctly classifies it as fake news. So let's say I have some article about Joe Biden declaring Trump the rightful winner of the election. And I want to think about some way I could maybe modify this input to actually cause the model to change its prediction from, let's say, fake news to real news. And so what we're going to do in this section is just show a simple attack based on this idea of inserting phrases into the input. So for instance, I could imagine this adversary which inserts, in this case, a very nonsensical phrase, maybe randomly in the middle of their article, which causes the Facebook algorithm to actually misclassify the input as real news instead of fake news. So a lot of people have seen these types of adversarial examples in past work. So hopefully people are a lot of familiar with these kind of input perturbations. But we're going to do that special in this kind of idea of universal adversarial triggers is this idea where you can actually find a perturbation that works for any input. And we'll see exactly what that means in a couple slides. So as I said, you kind of want to cause this specific prediction for any input from a data set. So in particular, like let's say imagine I have this same nonsensical trigger phrase that I showed on the previous slide. And then I have a bunch of inputs that are all, let's say, fake news documents about like vaccine ineffectiveness, about some fake death, and about USA winning the World Cup. In this case, what this trigger phrase does is no matter which input you insert it in, you can just kind of jam it into any of these inputs. It's going to actually change this fake news classifier's prediction from fake to real. So it's kind of this idea where it's universal in that it works across inputs. And this is really interesting, I think, from a couple aspects. And the main one, which I think people are excited about, is this idea that it allows anyone to fool models. So me as a machine learning expert and adversary, I could craft this trigger phrase, and then I could just post it on the web and allow other people to download it and similarly apply it to their inputs and sort of automatically enable them to do these kind of adversarial attacks. But they don't actually need to have knowledge of machine learning or even know what the heck the trigger phrase is doing. They just need to kind of insert it into their inputs. The other aspect, which I guess gets more at this kind of analysis question I mentioned previously, which is this idea that there's got to be something weird going on with this input because it's highlighting and getting at these kind of global input-output patterns. So like for some reason, when the model sees this trigger phrase, it kind of immediately jumps to this different prediction. So maybe if we do some sort of analysis of these triggers, we can actually learn a lot about what's going on under the hood. I think I maybe skip this part. So in general, the way we actually find these trigger phrases is using this kind of gradient-based optimization procedure. I won't go too much into the details of this procedure, but you can think about the basic idea of just kind of iteratively flipping words in an input until we find some trigger phrase that satisfies the criteria that we're looking for, which is when you provide it to any input, it provides a high classification likelihood for the label I want. So for example, we've seen a couple these instances, these trigger phrases, and this is actually how they work in practice. So maybe if you look at some classification task like sentiment analysis, or maybe something like fake news detection, maybe you have some trigger phrase like the one I mentioned of zoning, tapping, fines. And in this case, what we actually see is if you insert this trigger into positive sentences, what ends up happening is the model ends up misclassifying most of them as negative. So when you see this input, the model kind of just automatically changes its prediction to negative. And similarly for a different task like natural language inference, which is just another type of classification task in NLP, you also provide a trigger like nobody, and then the model's accuracy severely drops on the entailment class, so almost to 0%. So in general, these trigger phrases are these kind of, these series of words that we can insert into basically any input and cause the model's prediction to often change something that we care about. You can apply this exact same idea to different tasks. So I'll just provide a preview of like one task that you can think about is something like reading comprehension. In this task, you're provided some question like, why did he walk? And then you're provided some paragraph. This time it's about Nikola Tesla's exercise habits. In this case, the model says he walked for exercise, but you can also insert this kind of fake sentence, which is the trigger phrase that said, why, how, because to kill American people. And now the model thinks for some reason that he walked to kill American people. So you can imagine some sort of attack where, adversaries insert these sentences onto web pages on the internet. And then now all of a sudden, systems are responding to questions with, malicious phrases. Okay. The last thing I kind of want to talk about, so I just kind of talked about, what you might want to use these attacks for on kind of an adversarial perspective. I think a lot of the interesting things from triggers, and one of the reasons that I'm excited and other people are excited about it is this kind of analysis perspective, which is kind of analyzing why triggers actually work in practice. And so I think if you kind of do some more analysis and dig into the details of what's going on with these trigger phrases, we end up coming up with this idea about dataset annotation artifacts, which is also sometimes called spurious correlations or other types of biases in your data. And the basic gist is as follows. So in some data sets, exist these kind of known biases or artifacts where if you see the word nobody or sleeping or cats, you can almost automatically predict the label contradiction in this data set just because of the way it's collected. So for some reason, when you see the input cats, there's a really, really high chance that the label is actually contradiction. So models that are kind of lazy can just kind of see these words and just blindly predict that the label is probably contradiction. We're able to see that a lot of the trigger words actually overlap a lot with these known artifacts. So basically what this shows is that, we're able to identify these kind of vulnerabilities in models, and we're able to directly tie them back to sort of issues in the training data. So, you train on bad data, that leads to vulnerabilities in your models. And then actually these kind of adversarial examples really do expose some of these artifacts in the data. You can see a similar type of idea with question answering. I'll just mention a brief example where if you see something like a question, why something happened. So let's say I asked like, why did he walk or why did he something? And then what we see is the trigger often finds this thing of because of. So what we realize is that when the model sees the word because of, and it sees a question that asks why something happened, it often thinks, oh, why and because of, those definitely go together. So let me just say whatever phrase follows it is probably the answer. So you can kind of do a similar type of analysis for different types of tasks where, looking at these trigger phrases can actually tell you a lot about, what models are doing. Okay. Just for the sake of time, I'll just kind of wrap up this section, which is to say that we're able to see these trigger phrases, which do cause these kind of universal errors for numerous tasks. So basically, they're able to change model predictions for almost any input by just kind of inserting these phrases carefully in the input. And often we're able to use them to help debug our models and data sets. So a lot of times we find that these vulnerabilities exist precisely because of some issues in the training data. Cool. So just to wrap up the talk, I think we have a couple minutes left. We've talked about 3 different vulnerabilities of models. We talked about how one can extract training data from models. We looked at how one could actually steal systems that are behind black box APIs. And we looked at how adversaries can maybe control predictions by modifying their inputs. And some of the high-level takeaways is that, really hiding your model behind a black box API is just really not enough to protect it. So adversaries can learn a lot by just interacting with your system at test time and seeing its predictions for different types of inputs. We've also seen that things like memorization can occur even when there's little overfitting in systems. And there's kind of open questions around how to mitigate this undesirable memorization. We saw that distillation is just a really robust tool, which is what enables model stealing to work so effectively. And there's kind of questions around, can it be stopped without hurting your accuracy to a substantial degree? And we've also seen things like trigger phrases can automatically expose biases or spurious correlations in your data. And there's kind of questions of like how to prevent learning them, or how can we build data sets that don't contain these kind of undesirable biases in our systems. So I think with this, I'll end my talk here. Thanks so much, everyone, for coming, and I'm happy to take more questions.
Great. All right. Thanks, Eric, for the amazing talk. Are there any questions, comments, or feedbacks from the audience? And maybe I have fun about the third part of the talk, which is how is are you able to automatically detect a trigger somehow? I know you talked about some, sometimes we know a priori some words are good triggers, but is there a way, for instance, if someone wants to identify a new trigger, is it possible to do so?
Yeah, so I guess in general, we were looking at kind of a gradient-based way of identifying new triggers. I think sort of what you're getting at is like maybe another way of thinking about them, which is maybe you do data set analysis and then use that to kind of like identify triggers. So I think there's kind of two paths you can imagine, which is like starting from nothing, which is kind of what we did a bit in this paper of like, we kind of initialized trigger phrases with random sentences or short phrases, and then try to optimize them to fit the criteria. Another way you could imagine doing it is by digging into the data and then trying to find phrases that look anomalous according to the labels.
Isn't that like less of a black box attack because now you do assume as access to the data or like the gradient information as well, right?
Yeah. So in practice, I guess if you want to launch actually the attacks in a black box setting, you'd need to do something where you maybe craft a trigger for your own local model and then try to transfer it to some like target model. So a lot of the experiments I didn't mention that we actually had in the paper are about stuff like, how can you train a model that's similar to a target model and then, use that local version to try to like launch attacks.
Makes sense. Thanks. Yeah.
I had one question regarding the triggers. So you were saying that the intuition that you had about these in NLI tasks was that something very common as nobody would end up being wrongly termed as spurious. But from the experiments in sentiment analysis, it seems like words like zoners, which were probably not important at all, were becoming the triggers. So is there like a difference in the types of triggers that you see depending on the task?
Yeah, definitely. I think in the like NLI is one case where this stuff like really comes out very easily, mainly because like the data is super biased. In the sentiment case, I think like one thing that we definitely see is if you craft triggers for just one specific model, a lot of them are either due to something of like the model or the data. But if you craft triggers for an ensemble of models or some very diverse set of models, often you see a lot of these more like data patterns coming out if you kind of like marginalize over different models in that sense. So I think in the zoning tapping fines case, I think that's a good example of like if you do attack a specific model, sometimes the triggers can be like pretty nonsensical and like don't really tell you too much about like the data itself.
Cool. Any other questions or comments? All right. Yeah, with that, let's thank Eric again. Maybe give him a virtual round of applause for